How's it going, everyone? Welcome. Euler Gonzalez here. Today, let's going to explore now the other concepts from the functional programming, which are useful to make not only the code provable, but also easy to read, therefore to fix, maintain, and add some features. So that's the value proposition of this, because now since most of our code base will rely on this mathematical bedrock, mathematical proof, we can just focus on where our code has low level of, where do we have low level of confidence in our code. Most of the time that is on the side effects. All right, so and that's exactly the value proposition of the functional programming, which is taught by Kyle Simpson, this particular course. Shout out to Kyle Simpson. And this is a functional like JavaScript. Okay, this is his book, and we are actually looking at this different concepts or tools that we're going to add in our tool belt, like function purity, arguments adapter, point free closures, something that I am quite familiar with, similar as compositions, immutability, recursion, list operations, transductions, data structures operations, for example, like monoids, and we are now be familiar of stuff like Redux, for example, async and functional JavaScript utils. So today we're going to now walk through all of this concept, even look at the point free, so we can move on to the next topic, which is closure. Now, because in the previous video, when we explore about the nature of the function purity and why actually we need to look at this, and what is a function and a procedure and a functions, is the relationship between the inputs and the computed output. So unlike procedures where they might affect the state of the applications, functions, in a way to make the code provable, it need to be pure. In other words, don't affect the state out of the function scope. And there's some certain rules to do that, to avoid side effects. And side effects is anything that is cause or anything that changes the state of the application in an unexpected way. And that can be is network calls, input and outputs, reading a database, talk to the DOM, or a timestamp, generating random numbers. So anything can be boiled down to anything that generates CPU heat and CPU time delays. It can be considered as a side effect. So why do we need to avoid these side effects? Because now, if our function is pure, this will give us a high level of confidence that this function will give us an expected behavior. So anytime we pass the same input, we're gonna get the same output. This is also true, and especially when you're declaring function inside of another functions. The whole point of doing that particular pattern here, for example, like this, is to reduce the surface area in which a variable or a parameter can be reassigned. Why is that? Because when reassigns happens, it leads to unexpected behaviors. So this is the reason why we look here at function purity. And how can we create functions pure? Same input, same outputs. But sometimes in that pure functions, at the end of the day, we want to have, this give us now is levels of confidence, right? So sometimes there are inevitably part of our code that we need to do some side effects, okay? Read it to a database, the DOM, you name it. So how can we now extract the impurity in those cases? Now, functions purity's focus is on calls, okay? So what we care about in functions purity is functions call behave being in a pure way, not definitions. Again, it is important that what our focus here to write this code or to read this code is to make those functions to behave in a pure way. So to extract this impurity, there are several techniques, or at least these two techniques that Kyle Simpson show us. Okay, one of them is to extracting the lexical scope, which is here. You extract the lexical scope and you return a new value here. So in other words, you're saying, hey, by the time that you are now in here, by the way, we are creating is a closure. What does it mean is that these variables will be now reassigned on the scope change. So in other words, at the declared time, function declaration time, this is how you can have access to this. All right. However, and this actually will work because this is functions are hosted at the function level. All right. So you're gonna have this level at the top, and then the student. All right, so now by the time that you call this, you're going to get is now have access to the student. So lexical, let me actually show you this. So this technique of containing the lexical scope and pass that at the declaration time, so passing through the scope change, is one technique of how you can do that. And the other is extracting impurity via adapter, or in other words, is to take a snapshot of everything and then restore this and then restore it afterward. Why this is important? Because unlike the previous examples here, since we don't have any functions declarations inside of this function, all right, now we are dealing is with the dynamic nature or dynamic scope. So by the time that you call this function, which is the sort student by ID, no, I don't want to edit. I want to look at the entire code here. View file. Okay. So unlike this, containing the lexical scope technique and return a new copy, that's what it is. Okay. But again, we are containing is the lexical scope. In other words, we are creating is a scope change. That's how you can actually is to extract the impurity of this function. So by the time that you call this get student by name, you are now safely assume that this function will do one thing and one thing only. But the problem is that what happened when perhaps you can declare the function instead of these functions, all right, that you need to call at some point that function. So this is known as the dynamic scope. So unlike lexical scope, that this is known as the scope change, on the dynamic scope, this will be called here and it will create now its own function scope or function definition, it's going to create this function execution context that by the time you do this, it won't have this student will have access to the global scope. If that works on the global scope, if that student works at the global scope, then is when you have access to the student. If that doesn't exist, it will throw you an error. So why this is important? Because sometimes you might not have the ability to declare that function. You need to reuse that function. So in the concept of JavaScript, well, if I need to reuse this function, all right, or if I need to exactly reuse this function, and the only thing that I can do is to call that without declare the function's definition here, is say, hey, it's gonna take a snapshot of everything, a copy of that, and then return and then restore it afterwards. That's exactly the reason why we're doing is this. So far so good, because we know we hold is the student reference here locally. All right, so we now hold the student reference that we receive here, and then by the time that we call this, it will affect is the global. Okay, it will affect is the global student objects. So it's going to sort a global student object for that, and then you want to restore the state afterwards. So in other words, is with the original student that you capture in there. So in other words, what you're doing is take a snapshot of everything, okay, and then restore the state that was modified. That's quite interesting, because at the end of the day, you want this to return is a new state of this. So these two techniques, the lexical or to extract the lexical scope as it is, or to contain the lexical scope, or to take a snapshot of everything and then restore afterwards. The first works for functions declaration, which is good. The second works for functions called that are impure, like this, right? So this is a function pure. In other words, it modified, it caused a side effect. So you're gonna take a snapshot of everything, all right, and then you restore the state afterward to return a new copy. That's what happens here. That's what it is. So doing this small recap here, it now makes a lot of sense and also give us now level of confidence that this work will work as expected, that this function calls behave in a pure way, that the code is provable. It makes a lot of sense here, okay? And then we explore now several other concepts that are useful when it comes to now write our particularly functions. So in other words, is to make the code using all of these concepts and techniques to make our code provable. Otherwise, we're watering down the benefit of functional programming, and that is the arguments. So TLDR of argument is that on arguments we have we need to understand what an argument and a parameter is, despite that this being used interchangeable. But an arguments and a parameters is they're technically different. So parameters are the name of the inputs that you define in the function declaration point of view. So for example, here, the x and g, all right, they are parameters. And the other is the argument, which is the value that you pass when you call a function, on function call. So why this is important? Because functional programmers are obsessed, and we're trying to understand their obsession by looking and understand. So by looking at the function shapes, and that is the number of parameters and the shape of the number of things, parameters, the number of things and the shape of them that we pass in, and the number of stuff and the shapes that come out after it, or that come out of it. Okay, so that's the function shape, and these function shapes is pretty much like matching different Lego pieces, where by looking at the arguments adapters, and the ability for us to now modify is the number of arguments or the return value we receive. In this concept, most of the time functional programmers love unity functions, and the second favorite things is binary functions, okay, based on their arguments. And then you have now also is the additive. So why this is important? Because again, the whole point of this is to look at functions like Lego blocks, okay, where we want to match the shape of one with another. And because of that, because of these particular techniques, for example here, where we say, hey, we want to now is return a function that calls with one argument, or we want to return a function that call with two arguments. So no matter how much arguments you pass through this function, all right, it only going to take one or two. And this is true for also other kind of examples. Let me see if I put it here. This is known as the high order functions. For example, this kind of stuff. High order functions, which is, we have single order functions when we don't pass functions or return functions in that function. And high order function is when we pass a function or return a function. So again, the idea here is to look at the other examples here. So for example, flip and reverse. All right. Yeah, for example, flip and reverse. So flip and reverse adapter and spread adapter. Flip and reverse adapters. You got it. Flip and reverse adapters. Flip and reverse adapter. So this is the finder. Yes, it is. Okay. So this is the flip. And what it does, this flip is just, so this argument function adapters is to shift, or is to flip the first two arguments in a function. Okay? Flip.
A function and return. When I make G on line 11, that is the flip. That's an example of an adapter that I made that I might use. Not one you necessarily find, but it's an example when you find yourself messing around with the shape of your functions and they don't fit.
So this is another function argument adapter reverse that when you find yourself messing around with the shape of the function, you sometimes need to do this kind of stuff. So it's going to show this one. There you got it. There you got it. That's right. For example, reverse. It's like, hey, I'm gonna declare is this high order function where by the time I call this function that I receive initially, then I want to reverse their arguments, right?
Try to figure out, number one, can I change the shape of my function at definition so that it fits better? If not, can I make an adapter that changes the shape? Everywhere that we do this, we're looking for common patterns. The functional programmer is looking for the Lego piece that looks exactly like the Lego piece that they have a big old pile of. I want this thing to look like a Lego piece that I already have. I don't want to go invent new utilities all day, every day. Stop and think about that for a moment, because that may not be obvious. Why might I not want to just invent ad hoc utilities all over the place?
Mm-hmm. You might feel the temptation to create a bunch of HOF or a bunch of HOF utilities for functions shapes, but this is not recommended. Why? Because it is better for a community to go with standard tools to make things happen. Okay, that's why if you find yourself needing to create a new utility, you need to a new utility. You make a peer to your you make a peer to a popular functional programming. Okay. That's why if you find yourself needing to create a new utility, you make a peer to a popular functional programming. Okay. So everybody can use it, and it becomes a standard. So yeah, I know it makes sure.
Quite honestly, it's kind of creative and fun to do so. I can come up with all kinds of different shape-changing ones. Why wouldn't that be a good way of approaching my code base. And I would suggest to you that maybe why it's not such a great idea is because the whole point of being able to glance at something is the familiarity, the recognition of it.
Mm-hmm. It's better for a community to go with standard tools that make things happen. In other words, it is better to recognize stuff at a glance that we are familiar with.
Wherever possible, if the things that we're using are the known common things that every functional programmer for the last 60-something years have used, that's good. But when a functional programmer comes to your code base and they see this thing and they're like, what? I've never seen that Lego before. It's less familiar. So somebody has to spend more time reasoning about that math. Where it's possible for us to do so, we should try to make it recognizable at a glance. We should try to use the standard common ones. So that means get real familiar with at least one functional programming library and most of the methods that it provides. Once you've spent a few hours reading through the documentation for Ramda, for example, you're going to find yourself looking at a thing, seeing this shape and saying, oh, I know what that one's called. I saw that in the Ramda docs. Congratulations, that's functional programming. Instead of go invent your own and make one that isn't consistent and familiar, try to make it fit in with the existing patterns wherever possible. And when you can't, make your own. Document them well, put them in a standard library that the whole app uses, and use them as much as possible. That way everybody gets familiar with them. Another example of shape adaptation that we commonly do. You'll see this much more often than may be obvious.
Shape adaptation.
One kind of shape adaptation is I have a function that takes individual arguments, but I want to call that function with an array. It's expecting individual arguments, but here I have an array. What do I do? How do I get all the contents of this array into the individual arguments? Some of you may know about JavaScript's .apply method, which takes an array and spreads the values out as arguments. And there's a reason why that utility is called .apply, because
another
that's
function adapter utility.
Example of shape adaptation that we commonly
shape adaptation. Another shape adaptation. Yeah, another shape adaptation commonly used is to call is to call arguments. Yeah, another shape adaptation is that we commonly use is to call arguments individually or via an array. So for example, .call and .apply methods are part of the functional programming approach here.
You do. You will see this much more often than may be obvious at this moment. One kind of shape adaptation is I have a function that takes individual arguments, but I want to call that function with an array. It's expecting individual arguments, but here I have an array. What do I do? How do I get all the contents of this array into the individual arguments? Some of you may know about JavaScript's .apply method, which takes an array and spreads the values out as arguments.
Spread the
There's
array.
a reason why that utility is called .apply, because that's what functional programmers call it. When you take an array and spread it out as individual arguments, that's called an apply. Here I've called it spread args, called .apply, because that's what functional programmers call it. When you take an array and spread it out as individual arguments, that's called an apply. Here I've called it spread args, just so you knew exactly what it's doing. It's spreading the array of arguments out into individual ones. See how it does line 3, the dot, dot, dot? That's the spread operator. It is spreading out an array of arguments into individual.
Mm-hmm.
But that's exactly what JavaScript's .apply does. And it turns out the name for this utility, as you'll find it in almost all functional programming libraries, is apply. So the apply, G is the apply of F, line 11. It's the spread args that is the apply of F. So when I call G with an array, F gets individual arguments. Everybody follow me? Here's a little pop quiz. We're not going to actually show this code, but I just want you to play with this in your head, maybe type it in your code for just a moment. This is a pop quiz. If spread args is a function that can take an array and spread it out into individual ones, what's the inverse of that? What would unspread args look like? Unapply, what would that look like? I would be able to
take an
pass in
array,
individual arguments, and the underlying function would receive what?
An array.
Just think about that for just a moment. We'll just take like 30 seconds. After the pop quiz, I want you to think about, look at that spread args and think, how would I change this to do the inverse? It's not as complex as you might have thought. The dot, dot, dot operator on line 3, we simply need to move it from line 3 to line 2. We need to gather the arguments from line 2 and pass them as a single array, line 3.
We need to gather single arguments and then passing as a single argument. Exactly, and passing as a single argument.
That's it.
As an array.
That's the only difference between a spread args and a gather args, or an apply and an unapply, is whether we gather first and then pass the array, or spread and then, or take an array and then spread it.
And take an array and spread it.
It's the only difference between the two. And you'll find apply and unapply in all your favorite functional programming libraries. All right, so let's take a look at another aspect of functions. And this is kind of a higher level concept, and it may twist your brain a little bit, but that's okay. That's what we're here for. We want to push ourselves. So stick with me on this. Point free. What is that? I'd heard this phrase many, many times when I was trying to kind of pick up functional programming, and it sounded like one of those fancy, let's look at some other kinds of adapting my code base. And I would suggest to you that maybe why it's not such a great idea is because the whole...
Okay.
All right, so let's take a look at another aspect of functions. And this is kind of a higher level concept, and it may twist your brain a little bit, but that's okay. That's what we're here for. We want to push ourselves. So stick with me on this. Point free. What is that? I'd heard this phrase many, many times when I was trying to kind of pick up functional programming, and it sounded like one of those fancy concepts that I didn't know what to do and didn't know what that meant. But then I learned about it. I was like, oh, well, I've kind of already been doing some of that. And that's one of the gratifying sort of takeaways from a lot of functional programming, is that it turns out that this big idea of functional programming is another aspect of functions. And this is kind of a higher level concept, and it may twist your brain a little bit, but that's okay. That's what we're here for. We want to push ourselves. So stick with me on this. Point free. What is that? I'd heard this phrase many, many times when I was trying to kind of pick up functional programming, and it sounded like one of those fancy concepts that I didn't know what to do.
Yeah. Point free. What is this all about? This is a concept that we might be already apply, okay, and one of those fancy terms to describe and
didn't know what that meant. But then I learned about it. I was like, oh, well, I've kind of already been.
You know, this is a concept that we might be already applying, and one of those fancy terms that once you understand it, it is like, I now I get it. Now I get it. It's pretty much that. It's like, oh, but now I get it. But now I get it.
Been doing some of that, and that's one of the gratifying sort of takeaways from a lot of functional programming, is that it turns out that this big idea of functional programming is built up by a bunch of tiny little things, most of which we've already done, or at least we can find intuitive. It's rarely the case where you look at something and say, that is just so completely out of the realm of anything I ever would have thought or done that just totally mind bends. It's the combination of all those things that really pushes us into this different paradigm. So we're going to talk about this style of writing our functions. And this may sound a little strange, but it's a way of defining a function without actually writing anything in the function. It's a
yeah. So this is a way to define a function without, this is a way to define a function without writing actually writing anything in a function, without writing actually anything in that function. Bear with me.
It's a way of making a function by making it with other functions. That's really what point-free style is about. So what does this even mean? What does that name even mean? Well, I don't know if any of you remember this. I have a very vague recollection back to my 7th, 8th, 9th grade time frame, something like that, a long time ago. I remember a teacher saying something to the effect of fixed point functions.
Mm-hmm. So we have to go back a little bit in time. 8th grade, all right, and something like that, to where your math teacher mentioned, when your math teacher math teacher mentioned something about the effect of fixed point. Okay, when your math teacher mentioned the effect of your fixed point function. I quite barely remember that in Spanish.
We were doing something with our graphing calculators or something, and I don't remember what they meant by that. I have since Googled it and looked it up on Wikipedia, and I sort of now come to a better understanding. I wish they'd just said at the time more clearly, or I'd been able to understand more clearly what it was. But the idea of a fixed point function, remember back to our initial example we were talking about, we're motivating at the beginning of the course, the f of x and the 2x squared plus 3. Remember that function? Well, the idea there is that the input x outputs a y. What if that function had multiple inputs? What if it took an x and a y and it outputted a z? Well, now we'd have like a three-dimensional, it'd be a two-dimensional surface in three-dimensional space, right? The idea of a fixed function is that if you have more than one input, you take one of the inputs and fix it at a certain value. So for example,
in the following graph below, right? So for example, in the following graph below, like this, right? If for some reason we add now another parameter to our function, now this becomes a three-dimensional space, all right? So f of x, okay, is now something like this. So 3x power 3. I don't know how to make this to happen. This is format. Oh, that's interesting. Oh, crap. Anyway, like this, and then you say plus 2x times, yeah, plus 2x times 2 plus 3, am I right? So now if you add another, let's say if you add another parameter like this, so if you add another parameter, okay, now this becomes a 3, now this becomes a 3D, now this becomes a 3D in the space, okay? So the idea here is to fix a parameter that now we can is calculate based on the other so the idea is to fix a parameter and now we calculate based on the others. Okay,
I could say take a function that takes an x and a y and produces a z and fix the x at the number 3 for whatever reason. Now that's going to tell me
you say this one,
the line on that surface at exactly x equals 3.
okay. So if we fix the parameter, c to 1 and g to 3, all right, it will give us now a line of those fixed point or those fixed points on those fixed points dimension. Okay, holy moly.
That's mathematically what that was all about. So fixed point functions were where we took one of the inputs and we fixed it at a certain value. Well, that sort of speaks to why we're calling this point free, because point free definition is defining a function without needing to define its points.
So point, you know, it's like back to our example. So back to our code. This means so back to our code. Functions point free is that we can declare. Oh, I think it's we can is
finding a function without needing to. Well, that sort of speaks to why we're calling this point free, because point free definition is defining a function without needing to define its points.
Exactly. So functions point free is that we can declare a function without needing to define it is points, the data points or parameters. Data points,
aka its inputs. Without needing to explicitly define and map its inputs, can we define a function? And in a sense, it really ends up as a class or a family of techniques for defining functions by way of other functions. Okay, so let's take a look. some of you have probably done something like this. Many of you have passed in a callback, for example, like to this getPerson utility. I pass in this callback that receives line 1 an input called person, and it passes that along to some other function. In this case, to renderPerson. Anybody seen code like this before? Seen somewhat familiar. Okay, so this is very, very common. We receive inputs in one callback, we pass that input to another callback. That person parameter there is the point. It is the input. In mathematical terms, it's called a point for the onPerson function. And you notice that we've defined the onPerson function by specifically and explicitly listing out that point. So what if we could define the equivalent of that function without needing to list the point at all? Some of you may have actually done this before, and this is where, when I was first learning point free, I was like, oh, I've done that before. I just didn't know that was called point free. You might notice that the onPerson function taking a single input and the renderPerson taking a single input, you might notice that they have basically the same shape. Which means if they have the same shape, then they're interchangeable. Which means that I could just pass renderPerson as the callback. Anybody ever done something like that before, where you had this wrapper function and then realized, oh, I don't need the wrapper, I can just pass in the function? Well, if you've done that before, I have good news for you. Without you even knowing, you were doing this really, really cool thing that I'm going to give you this term, and you're going to be able to go back to your team and use this term, and you're going to sound really smart. And everybody's going to be like, whoa, that was really cool. What you were doing was called equational reasoning. That sounds cool, doesn't it? I'd like to put that on my business card. I'm an equational reasoning master.
I'm equational reasoning master.
It sounds cool. It's actually
pretty mundane. Equational reasoning. Un razonamiento, exacto. Un racionamiento ecuacional. This is in Spanish. Un ecuacionamiento, un razonamiento ecuacional. Equational reasoning. Razonamiento ecuacional. So, So, a lot of the time, we have seen functions like this. When we declare a function with when we declare a function with one single input or data point, okay, and return another function with the same shape. So since the shapes are interchangeable, okay, interchangeable. Okay. So since the shapes are interchangeable here, okay, we can just pass a function without declaring. Okay, we can pass a function without defining its inputs, data points. Okay, this is something known as equational reasoning. Reasoning, exactly. So it is It isn't just a fancy name to say I am thinking, or I am reasoning about that the shape of one function is equivalent in terms of its inputs to another function inputs. All right, equational reasoning. So the shape of the function, aka the parameters, the data points, their inputs, is interchangeable with another function with the same shape, with the same inputs.
Actually pretty mundane, okay? What's mundane about it is that we're basically saying if I have this thing that's got this one shape and I have this other thing that has the same shape, even if they do different things, if they have the same shape, then they're interchangeable.
So even if they do different things, if they have the same shapes, they are interchangeable. That's right.
Equational reasoning means reason about this thing and say that it is equationally, not equal like an identity sense, but equal shape sense with this other thing.
Is equal shape here. It is equal shape. It is equal shape with. It is equal shapes between functions. Equational reasoning. No, it is not. It is argument. It is shape.
Here we have an on-person function that is equationally, it is equivalent to the render person function, which means that we can pass render person. And the takeaway here is that we were able to get away with defining a function without needing to list the point. That's one aspect of point free, but I said it's kind of a family of techniques. So there are other things involved that fall under this heading of point free. And before I even show you some of these other more advanced techniques, I just want to warn you, it's like what I talked about in the intro to the course when I said that you'll be trying something and all of a sudden you'll cross this line from, oh, I was tracking with you, to like, what did he just do, right? At some point in the next slide or two, we're going to cross that line for all of you. It's okay. We definitely did for me as well, okay? But before I even show you, though, what I want to warn you is if you see this and then you say, as a response, well, I don't get that. That's not more readable. That's weirder to me, so I'm not going to do it. That's not the best response. A better response would be, wow, that's not what I was expecting. And it's going to take some time to get used to that. I should try that a bunch more. Okay? But on the other hand, another response, and I have seen this from folks, including myself, is that you see this and you're like, whoa, that's so cool. I'm going to do that everywhere. I'm just going to like point free everything. And you very quickly explode the complexity, the surface area of that complexity, way beyond your capacity to even understand what it is you've written.
Despite that this might looks awesome to include in your code base, this is a double sword edge that can increase the complexity in your code. That can increase the complexity in your code. So use sparingly.
So that's also not a great healthy response. The healthy response here is to push yourself a little bit, but fall back to things that are practical for you. And then push yourself a little bit more and fall back to what's comfortable and practical and readable and reasonable. And do that little by little by little. What I'm about to show you is the first time I saw it, I was like, ooh, I don't know about that. And then After a while, that became comfortable, and then my line moved a little bit. And then I tried a few more advanced techniques in point free, and my line moved a little bit. And then I tried a bit more, and a few months later, the line moved a little bit. So that's the way that's going to be for you. And particularly with point free, don't go overboard. Don't go overboard with it, because this is that point where my readability curve started tanking. It was with point free.
Mm-hmm. This is when your readability, readability start to decrease when you are new to this.
I was trying it because it was so cool, and I way overblew the complexity of it and lost all the benefits. At the end of the day, if your code is not more readable and understandable, then it's not benefiting. So what we want to do is we want to get to that idea of the shapes being equal with each other. Here I have an is_odd function. Pretty straightforward. It uses the modulo. Is we want to get to that idea.
So point free refactor. Equational reasoning. Equational reasoning. Because at the end of the day, point free is about equational reasoning. Is that this function's inputs are equal in shapes, in inputs, in data points with the another function. Therefore, they can be interchangeable. Therefore, you need to define the data points, their inputs. So an example of this. Okay. So what we want to do is to get the idea of shapes.
Idea of the shapes being equal with each other.
Okay. So here we want to get familiar with the idea of shapes being equal to each other. Okay, let's get into this. Let's definitely get into this. Let's definitely get into this.
Here I have an is_odd function. Pretty straightforward. It uses the modulo operator. So any value modulo 2, if it returns us 1, that means it was an odd number. If it returns us 0, it was an even number. Okay? Very basic math concept there. But if I wanted to find the is_even function, there's a couple of ways that I could have done it. I could have said is_even, and on line 6 I could have said v mod 2 equals 0. And that would work just fine. It's mathematically accurate to say that is_even is v mod 2 equal to 0. But I did it a little differently. I defined is_even in terms of the is_odd function. And specifically, I negated it, because we have a binary here. Something is either even or odd. It's not both, and it's not neither. It's either a number is either even or it's odd. So I'm asking the question here, if I take this is_even function and I define it in terms of is_odd, as opposed to doing just v mod 2 equals 0, what have I purchased with that choice? What benefit am I getting from defining is_even in terms of is_odd? To that idea of the shapes being equal with each other. Here I have an is_odd function. Pretty straightforward. It uses the modulo operator. So any value modulo 2, if it returns us 1, that means it was an odd number. If it returns us 0, it was an even number. Okay? Very basic math concept there. But if I wanted to find the is_even function, there's a couple of ways that I could have done it. I could have said is_even, and on line 6 I could have said v mod 2 equals 0. And that would work just fine. It's mathematically accurate to say that is_even is v mod 2 equal to 0. But I did it a little differently. I defined is_even in terms of the is_odd function. And specifically, I negated it, because we have a binary here. Something is either even or odd. It's not both, and it's not neither. It's either, a number is either even or it's odd. So I'm asking the question here, if I take this is even function and I define it in terms of is odd, as opposed to doing just v mod 2 equals 0, what have I purchased with that choice? What benefit am I getting from defining is even in terms of is odd? And the answer, I would say, is I have created a more visible relationship between the two functions. I have said that is even is the negation of is odd. Whereas if I just done v mod 2 equals 0, that relationship would exist, but it would be completely non-obvious. Here I am attempting to make it more obvious, the relationship between is odd and is even, by defining one in terms of the other. So it's not just about saving keystrokes. A lot of times you hear people say, well, blah, 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 dry, don't repeat yourself, right? That might be why a lot of people would justify, oh, dry, don't repeat yourself. I'm not saying that there isn't benefit there. Being unnecessarily repetitive can sometimes hamper the readability of a program. But actually, it turns out, sometimes in functional programming, it is better to be repetitive. So we don't want to take dry as like a religious, artifact, like, oh, I have to have every single thing written only once and everything is using the, the generic whatever. That's not always the best. Here, we're not doing is even in terms of is odd because we want to save a few characters of the modulo operator. We're doing it because we want to make it obvious that there's a relationship, a negation relationship between them. And by thinking that way, we actually got ourselves 90% of the way to being able to answer this question, which is, could I define the is even function in a point-free way? Could I define it in terms of is odd without having to list out that v that's being passed in? Because there's the point. This is a pointed definition, and we're asking, could I define it point-free? Before I even show you how to do the point-free,
yes,
we probably should have motivated what is the point of point-free? Like, what are we buying? Well, what we're doing is we're moving to that declarative style. When we have points, what we have is an imperative style that routes data from an input to an input.
So here, what you're saying,
point-free style, we have a declarative thing. Here's a strange phenomenon that I've seen with the idea between imperative and declarative. Because the words themselves, the physical letters in those words, to me imply that imperative would be implicit, since the words seem the same, but it turns out that it's reverse. It turns out that imperative code is generally more explicit, and declarative code is generally more implicit. Now, if you stop 100 software developers somewhere, and you ask them the question, is it better for code to be explicit or implicit? 99 out of 100 are going to tell you it's better to be explicit. And what we're actually suggesting here is that in some senses, it's better to be implicit. It's better to be declarative and allow the existing Lego pieces that are in our application, either in the language or in our library,
it's better to be implicit,
to handle those unnecessary details. Because it's not important for the reader of this code to see V on line 5 being passed on line 6. That is an unnecessary detail. If I can define this in a point-free way, I free up the reader to glance at and realize, oh, okay, is even is the negation of is odd. So how are we going to accomplish that? If you can agree with me that it is beneficial from a readability perspective, how are we going to accomplish it? Well, we're going to accomplish it by creating a utility that adapts the shape of a function. Exactly like we did before with hoffs, we're going to make another hoff. Actually, we don't need to invent one. One already exists. I'm just going to tell you about it. Let's think about it.
So we're going to take this function, and whatever is this is not, or negated.
So I like to use
so whatever function that you receive here, we're going to now negate it as a value.
It's called complement for something like random. But what it does, it takes the function fn line 1, it makes a new function that's negated, line 2, and all it does is call the original underlying function with all the inputs and return the output, but it does line 3, that little exclamation mark, it negates it. So now when I declare is even, I simply call this higher order function utility not, and I pass in is off. And what I would argue is not only is line 11 less to read and mentally juggle, because I don't need to see the function, calling another function, and passing a parameter, but it is even more clear the relationship between is odd and is even now, right? You can very clearly see that is odd is the negation, that is even is the negation of is odd.
This even is the negation of the other.
That's where we get the readability gains in functional programming, and specifically in point-free style.
And again, it's because at the end of the day, we are relying on this will work as expected, We're not relying on this, so we don't have any trust issues
you can
here.
almost stop right here at the, just get that, and you've got a huge.
So we don't have this trust issue here.
the key idea.
Oh, crap. Okay.
All right, let's do an exercise to practice these point-free refactoring techniques.
So that'll be all for this
exercise,
video.
you've been
Take
given
care.
several different functions.
Bye-bye.
README will